Let me begin with a word of prayer. So, Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, so let us continue with our work on the Lebesgue integral. Since you're all here, I will foolishly attempt to load top hat. You know? If I can get it. All right. So where are we? We are to stage 2. So here we go. Begin with a definition. The support. What is the support of F? So this is a measurable function. The support of a measurable function is defined to be the set of all points where F does not vanish. Right? He just says X, and he leaves the universe where X goes is being taken from up to your imagination. We should also say that F is supported on a set E if F of X is equal to 0 whenever X is not in E. Let's write that down. F is supported on E if F of X is equal to 0 whenever X is not an element of E. So I think it's helpful to draw a picture of this, you know. So if E is like this, right? If this is E, and I'm graphing the function in question, if it's supported on E, what does that mean? So it means that the graph would look like 0, 0, 0, 0, 0, right? And then it could still be 0 inside here, but, you know, something like this, for example. But it can't be 0 outside of E, right? Excuse me, it can't be non-zero outside of E. That's what it means for it to be supported on E. All right. He says, since F is measurable, so is the set sup F. Does that make sense? What does it take for a function to be measurable? What was it? It was F inverse of, how'd it go? Minus infinity to A, right? Measurable for all what? For all A? Well, I guess that was measurable on, wasn't that it? So here F is, you say F is from a measurable space to R? Huh? Oh. So why is sup F measurable? What's that? It's the complement of say it's E minus the inverse image of 0? Why would that make it measurable? So every singleton's measurable, and since E is I guess E is given to be measurable. Is that right? Since it's the All right. Well, I'm gonna move on. All right. So we shall next be interested in those bounded measurable functions. So our goal is to consider the functions f measurable with the bounded measure of the supplement, supplement is the support of f. So that's saying that the function's only non-zero on some sort of bounded set, right? Right? That's what this says. All right, he says, an important result in the previous chapter, Theorem 4.2, states the following. If a function is bounded by M and supported on a set E, then there exists a sequence of simple functions with each simple function bounded on M and supported on E such that, so this is Theorem 4.2. Let's see here, F bounded by M and supported by E then there exists a sequence of simple, what's a simple function? Bounded by M, I think. And supported by E. Such that phi n of x goes to f of x for all x. He says, okay, so what was a simple function again? Yeah, a finite linear combination of the characteristic functions on measurable subsets of E, right? So I think of it sort of like, well, I guess I'm still thinking of step functions in my mind, but I guess it's more general than that, right? Because the measurable functions could be like a set of points or something, right? It doesn't have to just be intervals. It could be more, it can be measure zero stuff as well. And then this brings us to lemma 1.2, which is the building block for what comes next here. Let's look at that. Lemma 1.2. F be a bounded function supported on E. All right. And this E has the measure less than, so E is a finite measure, all right? If, right, phi n equals 1 to infinity is any sequence of simple functions bounded by M, supported on E. Yeah. There's always more terms and conditions here. All right. Supported on E such that phi n of x goes to f of x for almost everywhere x, then point number 1, the limit as n goes to infinity of the integral of phi n exists. What kind of integral are we talking about here? 2, if f equals to 0 almost everywhere, then the limit as n goes to infinity of the integral of phi n equals 0. I'll be right back, guys. I got to grab some black markers. This is driving me nuts. Oh, I'm about to go back to the department without my magic pass. That would be very foolish. So the thing to think about here is we defined the Lebesgue integral of a simple function last time. That's why we can say what we've said in level 1.2. I'm back. All right. So he says, the assertions of the lemma would be nearly obvious if we had the phi n converge uniformly on E. Instead, we recall one of Littlewood's principles, which states that the convergence of a sequence of measurable functions is nearly uniform. Right. So I guess we're going to use Agarov's theorem. Let's see here. He says, since the measure of E is finite, we can take epsilon measure of E is less than infinity given epsilon greater than 0 by Egoro, Agarov's theorem, right? There exists closed measurable set A sub epsilon, right? Subset of E such that what? The measure, well, E complemented by this closed set is not that big, right? It's at most epsilon. and phi n goes to f uniformly on this. Okay. I think that is literally the, isn't that what that theorem said, or no? I mean, is there epsilon between Egorow's theorem and our application of Egorow's theorem here, or what? So it really is just. So instead of the f sub k, we have phi sub n. But what were the phi sub n's? The phi sub n are measurable function. I mean, the phi n are measurable functions, right? These sequence of simple functions. I think I maybe was supposed to say, is there such a thing as a simple unmeasurable function? Or simple functions by assumption measurable? Okay, so that fits the terms and condition of, Egorow's theorem. Sequence of measurable functions on a set of finite measure converges to f almost everywhere. Then given epsilon greater than 0, we can find a closed set A sub epsilon, subset of E, such that the measure of the complement of the set by the closed subset A sub epsilon is less than or equal to epsilon. And yeah, it is literally that theorem so far. Okay. Then what? He says setting let In equal to the integral of phi n. So this makes sense because we've defined remember we defined the Lebesgue integral of a simple function last time? So that is a well-defined thing. We can talk about it. And what we're trying to do is trying to show that, I guess part 1 and part 2, that the limit as n goes to infinity of this thing converges, right? So he's looking at the difference of In and Im. I'm guessing he's going to show it's Cauchy, which probably would be helpful since it is a sequence of real numbers. So the absolute value of In minus Im is less than or equal to the integral over E of, okay, so this is what was this property? What was this called? You guys remember this property? What do we call this property? What's that? Was it triangle inequality? Is that what we called it? Yep, that is right. So that was part 5 of proposition 1.1 on page 51, applied to, in this particular case. I mean, so actually it's a couple different things, right? I mean, to be clear, really, first of all, we have the integral of phi n minus the integral of phi m. Then by additivity and homogeneity, we can combine them into a single integral, and then we use the triangle inequality to do this. Okay. Then what? Ooh, look at this. He says that is, oh, I see. Check this out. So what he's going to do is he's going to break it into 2 pieces, yeah? The piece over A epsilon plus what? So if you want to break E into 2 pieces, you take this piece and then the complement by that piece, right? So that's everything, right? That's just that integral of a union of disjoint sets is the sum of the integrals over the union of the disjoint sets, right? I mean, the thing I was puzzling over at the end of last class as it relates to the Riemann. Let me put it in terms of, specifically, I'm using part 3, the additivity. I just said we were using additivity in the previous set. I should have said, he calls it linearity. Linearity for the integrand, additivity for the bounds. This is whatever, I don't think that terminology is universal, but then again, what do I know? So what can we do? So next up, So that's less, you guys tell me why this is true. Two times m times the measure of E minus A epsilon. Where's twice the measure coming from? Oh, okay, very good, very good. I was thinking something like, I mean, I agree with you. I was thinking about something like this, you know? A very greedy. I mean, this is actually not the case. The equality is not the case, right? Because sine and cosine are never simultaneously 1 or minus 1. But, you know, this is often at times a useful and greedy way of obtaining inequalities for sine and cosine. Just assume they're all 1. It's the worst possible case, right? And similarly here, if they're both m, it gives you 2m, which is the triangle inequality. That's the justification of it, yeah. So because these are both bounded by m, by assumption, we get the 2m. And then the integral of dx over this is what? I mean, m dx, well that is equal to m times the measure of that. I'm trying to think if that was made clear in the previous story arc. Does he, I guess that might be an exercise or something. If we have a constant function, right, then that's a simple function of a kind of stupid kind. And so you can just calculate the integral by the definition to be, I mean, this is essentially the definition of the Lebesgue integral for the simple function m over that. You know what I'm saying? Do you guys understand what I'm saying? The simple function I'm talking about, phi of x, is equal to m times chi E minus A epsilon. When we integrate that, we take m times the measure of that. That's the definition of the integral over a simple function. So the integral of a constant over dx is just the constant times the measure of the integration region, which is what I have here. Okay. It is kind of amusing, right, how the integral of a constant works out in this Lebesgue definition, isn't it? I know, I think it's kind of funny. Now this, by Inequalities theorem, we already know this guy is what? Less than or equal to epsilon. So what's that show you? He says, okay, he says, by uniform convergence, one has for all x in A epsilon and large n, oh, you can make this, you have control of this, right? You can control this, right? For n much, much greater than 1, you can make that as small as you want. So since you can make that as small as you want by the uniform So since I can make that as small as I want, and I can make that, of course, that small, then it follows that we can make the difference between in and im as small as we want, which proves that the sequence in is a Cauchy sequence. Therefore, it is a convergent sequence since we're working with a real sequence. And it follows that the limit as n goes to infinity of the integral of phi n exists. Does that make sense? I hope. Then what for the second part? He says for the second part, if f is equal to 0, we can repeat the argument above to find that, He says if f is equal to, I don't quite see where f entered into the fray here, did you? He claims that if f is equal to 0, we can see that in minus im is less than or equal to the measure of E times epsilon plus 2m epsilon. Can you guys explain that to me? Because I didn't write f anywhere in here. I mean, we use the uniform convergence of the phis to argue that this could be controlled and made small. I guess if this goes to 0, right? Well, almost everywhere, though. It's not identically 0. It's 0 almost everywhere. How do I get that? So you say pick n much big enough, right? For epsilon greater than 0, right? Pick that such that, what do you say, that the absolute value of what? That?
Yeah. Less than epsilon.
Uh-huh.
Although I don't know if uniform convergence implies that Cauchy uniform. Like that inequality is true for all x for x in A epsilon.
I mean, what does this give us precisely? Doesn't that say that, yeah, for all epsilon greater than 0, there exists n, big N rather, and the natural number is such that n greater than or equal to that big N, right, implies, yeah, that the absolute value of phi n of x minus f of x, right, less than epsilon. So that would be, of course, for what? For all x and e, right? See what?
That's what the theory said.
Yes.
Okay, epsilon better.
Oh, this is only for epsilon.
But it's close.
It's what?
Well, it's close. Like the measure of p minus k epsilon is small enough, so p is going to go around.
But technically, this is for all x in a epsilon, you're saying. So that means that I can only apply that to this piece.
Well, rather you use double p n x minus fx and p of x minus fx and add it to this.
You're talking about this part, this piece? Oh, so you're saying I play the adding subtracting game? This game, right? All right. So that, but I guess the thing is we could have, since we have uniform convergence for all epsilon greater than 0, for the epsilon greater than 0 that we're interested in, we could have made this epsilon over 2, yeah? So, ah! Which would be, oh, but that's not quite it either, is it? I mean, that gives me, what's that give? Okay. It's not, he's got the measure of E up there. But I guess that's the thing is, since A epsilon's a subset of E, this is less than or equal to, right? And somewhere we need to use the almost everywhere. Yeah? Well, that's the thing is, we don't have that it's equal to 0 everywhere. We have that it's equal to 0 almost everywhere, right? So that's getting used in here somewhere too, I think, right? No? Is that right? No. I don't see how I used f equal to 0 here, do you?
No, I was wondering where so you don't even have x over here.
So this is he's got a sentence after the original argument, which I,
Oh, there it is.
he says, for the second part, notice that if f equal to 0, we may repeat the argument above to find that the,
Oh, that's where it converges. We have the piece of n goes to f.
so I'm an idiot. I can't even follow instructions. He doesn't have the difference of im and in here. He just has just that. Right? Because, oh. I mean, that wasn't wrong, all right? But we didn't need all that. We just, this, hmm? But, well, I actually mean, no, I mean equality up here because that's 0 almost everywhere. It's 0 almost everywhere in E, and therefore it's 0 almost everywhere in A sub epsilon, just the same. And so I think that makes this step make sense because the okay, so you're saying this is almost everywhere. I need almost everywhere here is your point. Okay. And so, oh, but this is bounded by epsilon, right? And so finally we get, this is just straight up measure of, well, epsilon times the measure of A epsilon, which again is less than or equal to epsilon times the measure of E because, and so that's, what happened to where'd the 2m epsilon come from? Oh, because we still have this piece, right? So I'm just looking at this piece of it. This other piece, there's no subtraction. You just have integral of phi n over the complement of E by A epsilon, which is bounded by, it's easier for me just to write it out. I'm sorry, I'm spending entirely too long on this piece of it. I'm sorry. I should go on. So this is less than or equal to the integral of m dx, right? Which is m times the measure of E minus A epsilon, which by Egorov's theorem is less than or equal to m epsilon, right? And there shouldn't be a 2. There's not a 2 here. Oh, there's not a 2 in the book either? So I invented that 2. So if I could read, the 2 wouldn't be there. Yes, okay. But I shouldn't try to read and talk. Oh, Kang's like, 2 is not wrong. You can always add another. It's just an estimate. Fair enough. All right. So I hope we have lemma 1.2. I'm going to erase this so I can't hope to fix it anymore. I know we don't prove everything in here, but I wanted to prove something here and there, so at least we have some sense of, it's not impossible, it's just a matter of time that we don't quite have, The time to do these sorts of things, it is possessed by these creatures called grad students. Let's see here. Where was I? All right. Oh, definition. Woo! So this leads us to a definition. The integration of a bounded function that are supported on sets of finite measure. For such a function f, we define the integral of f of x dx to be the limit as n goes to infinity of the integral phi n of x dx. So this is for f of x, I guess technically speaking, maybe there should be an E here, yeah? For f of x, for f bounded on measurable E with the measure of E being less than infinity and f supported on E, right? Actually, I guess if f is supported on E, if there was a larger universe in which E fit, you'd still make this the definition of the integral. Right? I mean, does that make sense to you, why I'm saying that? If, if this was E, right? And so we can kind of visualize f has got some little, I don't know, whatever. It pops up out of the plane there, but it's 0 elsewhere, right? It's outside of E, f is 0 everywhere, So if there was a larger universe in which E fit, then I would still say that the integral over that larger universe of such a function is still just the integral over E, because that's where all the non-trivial contributions to the integral are coming from, right? So maybe that's why he's being a little bit cagey about where the integral's taken over, because it doesn't matter if it's just over E, or if it's putting E in some larger context. Either way, it's the same, because f is by assumption only non-zero inside E. All right. He says, well, next we need to show that f is independent of the limiting sequence phi n used in order for this integral to be well defined, right? So let's suppose that we had, for this definition to make sense, for our definition to survive logic, we need its value. I just want to put an apostrophe in its value. What's wrong with me? To be independent of the sequence of limiting simple functions a la lemma 1.2. All right. So consider another sequence of functions. Let's say psi n is what he says. All right. Such that psi n goes to f, right? And the phi n goes to f, right? So suppose you got two sequences of simple functions, both of which converge to f of x for almost all x as x tends to infinity, all right? So let me be more sorry. Limit as n goes to infinity of psi n of x is equal to f of x almost everywhere. The limit as n goes to infinity of phi n of x is equal to f of x almost everywhere. And we're assuming both psi n and phi n are a sequence of simple functions that are subject to the terms and conditions of lemma 1.2, right? The given f is bounded, supported on a set of finite measure, and this is a sequence of simple functions bounded by n. All right. So I think what he's going to do, as is often the case when we're trying to prove uniqueness, is look at the difference of the two candidates, right? Because if we could show that that's 0, then we'd be in business, I believe. So he says, let a to n equal to phi n minus psi n. So what is this? What can we say about this a to n? So is the difference of simple functions a simple function? It is. All right. And, okay, great. So then the limit as n goes to infinity of a to n of x is what? F of x minus f of x, right? Well, whew. That's not quite how he argues. He has a better argument. I'm sorry. He says it's a simple. He says that the sequence a to n consists of simple functions bounded by 2m and supported on a set of finite measure, such that an goes to 0 almost everywhere as n goes to infinity. I guess that's what I'm arguing right now, is that this, because we have limit law here because they both exist separately, right? Let me just get to the point. This is equal to 0 since both of these, go to f of x, which then cancels almost everywhere, right? So we have a to n goes to 0, and also what? A to n of x is less than or equal to what? Phi n of x plus psi n of x, but those are both bounded by 2m. I mean, m and m, so 2m. So what is this sequence of we have a sequence of simple functions a to m, bounded limit to the 0 function. So what's that say? So by 2 of lemma 1.2, what do we get? So I think we need to think of this as our f. Okay, the limit what? N goes to infinity of the integral of a to n equal to 0. But this is tantamount to saying what? Right, using the property of the integral over simple functions. So there you go. We have uniqueness of our choice of representation for our bounded supported function. So we survived logic. That's good. Okay, great. So he says, so if E is a subset of Rd with finite measure and F is bounded with the support of F being, finite, then it's natural to define she says integral. Oh, I guess I already did it, right? But, well, maybe I did it badly. He says the integral of E of f of x dx then should be understood to be the integral of f of x chi of x dx. So I guess the integral without adornment is taken over what? In this wild world of fancy integration. What's an integral without bounds? Where is it taken over? Yeah, I think the whole space, right? And that's okay because the thing we're integrating is only finite over part of the space. Despite the infinity of the space, the finiteness of the thing we're integrating kind of still makes it make sense. All right. Then he has proposition 1.3. He says, suppose f and g are bounded functions supported on a sets of finite measures, then we have the following properties: linearity, additivity, we write them down. So f and g bounded on sets of finite measure the integral of AF plus BG is A integral of F plus B integral of G to, if we have the integral over a disjoint union of F, the integral over F of E plus the integral over F of big F, monotonicity. What does this mean? F less than or equal to G? What does that mean? Can you tell me? So I think this means that f of x is less than g of x over the domain of consideration, right? Oh. So these should all be familiar, right? Because these were all the properties that we had before for the Lebesgue integral defined on simple functions. All right. He says, we are now in the position to prove the first important convergence theorem, bounded convergence theorem. All right. So let us at least write that down. Theorem 1.4, bounded convergence theorem. Suppose that Fn is a sequence of measurable functions all bounded by M. All right. And supported on set E with finite measure. All right. Man, so much fine print here, you know? And Fn of x goes to f of x almost everywhere in x. Well, that's not the way to say it. I'm just going to say it almost everywhere. I don't know. Almost everywhere as n goes to infinity. Then f is measurable, bounded, supported on E for almost everywhere x, and the integral of the value of Fn minus f goes to 0 as n goes to infinity. Consequently, the integral Fn goes to the integral of f as n goes to infinity. Oh, so much writing. I'm excited because we are almost to the point of discussing the Riemann integral. We just need to discuss this, and then that's next up is the Riemann integral, right? So what do you guys think here? What is this theorem saying? Can you kind of just talk me through it? Am I going to regret erasing this? Maybe. Possibly. Uh-oh, I've offended Jonathan. Let's see here. Let me just step away from the board for a second, where I can read it. So suppose Fn is a sequence of measurable functions, all bounded by m, supported on E, set of finite measure. Fn goes to f of x almost everywhere, as n goes to infinity. Then f is measurable, bounded, and supported on E. And the integral of the difference goes to 0, consequently that. So I guess this is saying that the limit of a sequence of bounded, measurable, supported functions is again such a thing. So that's and also that and furthermore the integral of it exchange the limit. So this could be rewritten. This could be rewritten the limit as n goes to infinity of the integral of fn of x dx, right, is equal to the integral of the limit as n goes to infinity of fn of x dx, because that is by construction right. So I mean, that's what this consequently is saying. It's saying we can exchange the order of integration and the limit. Yeah. All right, so how's this proved? Let's look at the proof. He says the proof is a reprise of the argument in lemma 1.2, again using Igarov's theorem. So I think I'm just going to, I won't write the whole proof out. I'm just going to write down the critical inequality. We'll look at that. Oh, I should probably leave that for, for Jonathan, yeah. So the critical inequality to understand the proof of the bounded convergence theorem is what? So the key inequality for proof similar to lemma 1.2 is this: the integral of the value of fn of x minus f of x dx